Thanks, Jeff. For the next button, just push the mouse. Okay, or the right. Okay, thank you very much. So I'll be talking about the first portion of this, which we were looking at climate change and then future projections of climate, how those impact fluvial hazards along the Northeast Entrance roadway. So the outline today, going to kind of go over that process with the ultimate goal of assessing our assets, which is the linear roadway, and then our improvement alternatives to provide a comparison of those relative to each other. We're going to identify and characterize the fluvial hazards, both under current and historical conditions, but also into the future and how those change and would help drive future fluvial modeling. So flood risk assessment is shown here. This portion of the study focuses on those top two pieces there with the identification of those hazards and then the assessments of those hazards, so historical conditions. On the right here, what we're showing is the sources of data for all of that. So historical came from a variety of sources with data dating back to 1895 up through 2022. And some of them were more complete than others. Again, as data comes, it's hit or miss. We use the Oregon State PRISM network. We also use LOCA data, which has historical data to help drive some of those climate models. Climate Toolbox was also used, which uses a CMIP5 data, which is based on historical conditions. For gauged and ungauged streamflow data, we used StreamStats and USGS. And we also use NOAA for the precipitation. In terms of future conditions, we were looking at two different points in time in the future, 2040s, which we characterize as mid-century, and 2080s, end of century. The data that was associated with those was resulting from the LOCA, which is a localized coupled analog. It's downscaled global climate model data from CMIP5. And we also use the Climate Toolbox and from the University of Washington's Climate Impacts Group for extreme precipitation projections. So the first part of this process, we're going to identify those fluvial hazards and then characterize them to existing or historical conditions. For the extreme precipitation, what we're showing here came from NOAA Atlas 2, which is an older isohydral set of maps that provide between the 2 and 100-year design storm depths. So they ranged in the Yellowstone corridor along the roadway. These points were taken along the roadway between 1.5 and 3 inches from the 2-year up to the 100-year event. This is 24-hour duration. The two plots, the top right is showing you the monthly average precipitation that can occur, with about 8 inches of rainfall occurring in the springtime months between March, April, and May. That's about 9% of the annual rainfall that's occurring. Below is the annual, so the average annual. You can see it's a little bit sinusoidal in terms of wet years, dry periods, wet periods. The trend overall, though, slightly hovering around zero change, slightly increasing in terms of annual precipitation. There's that little arrow there. So with snowmelt and rain on snow, these can be a large driver for in-stream flow rates when we get runoff from snowpack, but also from rain on snow events. So we use snow water equivalent, which is how much water is located in the snow itself on an annual basis. You can see that red line is the 10-year average. So we're assuming that snow water equivalent represents the maximum amount of snowpack that would be present in a given year. And we were using this as the basis, which is around, I think, 15 inches on a 10-year rolling average. The bottom left is showing you the average monthly stream flow for historical conditions. And when we say low, medium, and high, I'll get into this later, but it's representing the ensemble of historical conditions. So the 10th percentile, 50th percentile, 90th percentile. What that shows us is snowmelts occurring in the springtime months, starting in March, and then ramping up and maximizing by June, and then petering off as we get into the summer months. This is a springtime precipitation, so slightly increasing trend in precipitation from the data that's shown here historically. And then this is just another of the annual or the monthly precipitation showing you how much is a function of the annual for springtime precipitation. So for runoff and in-stream flows, what we're seeing here are the daily runoff at a watershed scale. So how many watershed inches of runoff would occur from the Yellowstone headwaters watershed. That's the ICOET level. This is showing the 10-year average, so it's going over time. Again, some ups and downs through time, but also increasing over time as well. What we see on the right is the average monthly runoff. So again, similar to snowmelt runoff, the in-stream flows experience a peak between March, maximizing in June, indicating the driver there. The USGS gauging station, there were 3 within our Northeast Corridor entrance with the USGS. This one is down near the confluence with the Yellowstone River. So this is down where the road tees in with the main road. And just showing you just some comparisons in terms of peak flow rates of the 100 up to the 500 year. The USGS identifies that 500 year is about 22,800 CFS. And when that June 2022 event came through, it was very close with about 21,400 CFS. So it was on par with the 500-year event. So now we're going to take our fluvial hazards. We're going to assess them relative to future conditions and what the probability of change for those would be. So giving you an overview here, we were using existing CMIP5 and LOCA data, which is global climate models downscaled. What this is showing is some of the model projections which use the RCP, or representative concentration pathways, and that's it's just choosing how much greenhouse gases there are, and then what we chose with the guidance from the client was the RCP 8.5, which is here, the top one. That's a business as usual case, which is what scientists believe is the more likely scenario to occur over time. And so we chose that at the 2040s and 2080s time periods in the future for mid and end of century. And then again, the low, medium, and high scenarios were chosen in terms of what model results were picked, the 10th percentile, 50th percentile, and the 90th percentile, to show the range, because with these types of projections, it's good to account for an ensemble of the results and then use that to show where any uncertainty in the data projections may occur. Extreme precipitation shown here. The 3 figures on the left are showing you the seasonal responses. Between historical conditions on the left going all the way to the end of century or 2080s on the right, we show increases in those seasonal precipitation amounts for winter, spring, and fall to a lesser extent, and then reductions in the summertime. You can see the spread of the data here with those bar charts. For the extreme precipitation, in the middle, what we're showing are the future design storm events. And this is a function of these 2 plots right here, which were taken from downscaled projections from the climate models between the 2 and 100-year event. So a tighter range in terms of where the changes may occur on those smaller, more recurrent events, up to greater uncertainty in some of those larger events. But what you're seeing is by 2040, you have an increase in precipitation by about 6% to 25% of that, which we've translated with the blue and orange values here, to 10% to 30% by the end of the century. So it can be a rather sizable increase in terms of precipitation on an extreme event basis. In terms of temperatures, we see warming conditions by end of century. So what we're seeing here in the top left are days where minimum temperatures exceed the freezing point, 32 degrees. Historically, down there around 108, but we increased to 170 days by end of century. So increasing that by 60 days, which means less cold weather has an impact on snowpack potentially. For annual minimum temperatures, we see a decrease in the number of days, as well as a decrease in the temperature in degrees Fahrenheit, increasing by 10 degrees up to 31 degrees Fahrenheit by end of century. And on the right, we see springtime minimums and springtime maximums. So this is a seasonal approach, looking at an increase on the order of 9 to 10 degrees. So colder days are getting warmer, warmer days are getting warmer. In terms of projected snowmelt, so taking these into account, as we have warming temperatures, as we have more precipitation falling, we see a higher probability of precipitation falling as rainfall in wintertime conditions. So we have less snowpack to draw upon. But when we look at how that snow melt is changing, what this plot here is showing on the bottom left is the difference in average monthly snow melt. So typically we would see a March to June increase. Now we're seeing an increase in the snow melt coming earlier in the year, in January, February. Looking at all of those models starts to ramp up and have a greater increase by April. And then what you see on the right side of that plot is a decrease in late spring and early summer snowpack runoff, so snowmelt runoff. Taking that into account with increasing spring precipitation by the end of century and increasing percent chances of extreme events occurring, this does lead to an increased probability or likelihood of springtime rain on snow events occurring more frequently in the future. So for our projected runoff, we downscaled the locus CMIP data and did some analysis on it to estimate percent changes in runoff as well, which helped to drive the fluvial modeling and projections in terms of flood extents and peak flow rates. We used the 32-member ensemble, so all the models were taken into account, looking at that low, medium, and high value. And what we're seeing here in this plot is a percent change in the daily runoff data. But for both the medium and high conditions, we're seeing an increase in the daily runoff at the watershed scale for less frequent, larger events. So the 1 would be related to a 100-year event, 10 is a 10-year event, so this is the probability of recurrence. And so you see a reduction in the less common or the more common events between the 1 and 10-year, and more likelihood of larger events occurring with greater flow rates. Projected stream flows, what we're showing here are the log Pearson plots for the 3 different gauging stations. And we're going to look specifically here at Soda Butte Creek at Trout Lake. So if we take the 100-year event and we trace that up to the baseline condition in black, that tells us that our 100-year event at this point is typically about 2,700 CFS. When we trace that up based on the projected percent changes in runoff and stream flow, we are showing that to increase to about 3,600 by end of century. So that is showing an increase not only in the peak flow rate, but when we look at the recurrence of this, an event on the order of 100-year recurrence today in the future could potentially be occurring more on the order of 25 to 50 years in terms of a recurrence level. So finally, characterizing our future fluvial hazards. Why is this important? Well, we were using this to help drive percent changes in peak flow rates, which Craig then was using for some of his models to estimate some fluvial characteristics of the stream and corridors. And just a high-level takeaway, so what we were seeing was average and extreme precipitation was increasing both in terms of magnitude and in frequency, so greater recurrence of these larger events. We were seeing average and extreme temperatures increasing in time, so that has an implication for a longer growing season, which drier summers have the implication for greater wildfire probabilities and debris flows. So you can see how it's all connected. And with snow water equivalent, we're showing that projected to decrease with more precipitation falling as rain in the wintertime months, and then a shifting in terms of that peak magnitude earlier in the year, earlier in the spring, and then less stream flow to draw upon in the summertime months, which has implications for in-stream flows. Finally, shifting hydrographs. Oh, just spoke about that. Sorry, got ahead of myself. But now I'd like to hand it over to Craig. Oh, Q&A first. Yeah, we're going to do a Q&A in between. Yeah.
Thank you for a very impressive presentation. I'm not sure I'm really smart enough to ask you the question. I'm going to try it anyway. So you showed a graph that shows the peak of the snow melt in June. And then you showed another graph that showed the degree of the change. I'm not sure exactly what the units were. Does that elongate the curve? I mean, you got the same area under the curve, but it's a longer curve. I would think the peak would be lower. You know what I'm saying?
Yeah, so that was showing the percent difference on that second graph. So yeah, so it'd probably be bringing the lower part of the hydrograph up, lowering the higher part down since it's decreasing.
Yes.
So flattening it out a bit. We didn't do that analysis, but that in my brain, what a hydrograph would do if you're reducing and increasing flows in various areas. So yeah, does that answer your?
Yeah, so I'm just like to see it.
Okay. If you give me your card afterwards, I'll make one for you.
Do your models assume or take into account whether there's a snowpack being lighter?
Interesting. So we were using downscale data from models that we didn't build, but we were using data from the VIC model, which is variable infiltration capacity. And so that snow water equivalent would account for wetness in the future. So I would assume it would be bundled into that value. Yeah.
Okay, thank you.
Thank you.
you.